So again, with solution stoichiometry, we're given either some information about the concentration of a solution, or we're asked to find the concentration or volume of solution. So we'll be doing the similar processes with if we're given mass, just slightly different. So here we want to find the volume of a 0.110 molar solution of hydrochloric acid necessary to react completely with 3.75 grams of aluminum hydroxide. So we have this mass of aluminum hydroxide. We want to know how much volume of a 0.110 molar solution of hydrochloric acid we need to react completely with all the aluminum hydroxide. And so just to kind of recap, molarity, I'll write it over here. Molarity is moles of solute divided by liters of a solution. And so in this problem, we're looking for the volume, aka liters. So I'll put a V there for volume. So to find the volume of solution, it's going to be the moles of solute divided by the molarity. So if we know the moles of solute and we know the molarity of hydrochloric acid, we can find the liters of solution, aka volume, that we need to react completely with that amount of aluminum hydroxide. And so from the problem, we know that molarity is given to us. So the molarity of HCl is 0.110 molar, but we don't know the moles of HCl. So that's our question mark. And so we have to use the other information to determine the moles of HCl. One other important thing to remember is that we want to know the volume in milliliters. And so notice here, this is liters of solution. So once we find the volume, we're going to have to convert it to milliliters to get it in the right unit. So now we have to use this 3.75 grams of aluminum hydroxide to find out the moles of HCl. And so if we reflect back to our previous chapters, if we have the mass of aluminum hydroxide, we can convert this to moles of aluminum hydroxide, and then we can convert it to moles of HCl. And so this is how we're going to find the moles of HCl, and once we find the moles of HCl, we can determine the volume of HCl solution we need for this reaction. So we set up our train track. So we start with the mass of aluminum hydroxide. Now we want to convert that to moles, so we divide by its molar mass. Now we have moles of aluminum hydroxide So now we look at the ratio between aluminum hydroxide and hydrochloric acid. So 3 moles of HCl is needed for every 1 mole of aluminum hydroxide. So it's going to be a 3-to-1 ratio. So 1 mole of aluminum hydroxide gives us 3 moles of HCl. So now everything cancels but the moles of HCl. 3 or 4 significant figures will suffice for these types of answers. So we get 0.1442 moles of HCl. Now we know the moles of HCl. So now we know the moles, we can find the volume. The volume equals moles divided by molarity. So we get 1.311 liters. So once the answer in milliliters, so we have to convert liters to milliliters, and we get 1,311 milliliters of this solution is needed. So you'd have to measure out 1,311 milliliters of a 0.11 molar solution of hydrochloric acid added to aluminum hydroxide, and you would completely use up these 3.75 grams of aluminum hydroxide. Number one, we already did a problem like that, so we're going to skip number one. That was similar to what we just did, so I'll just cross that one out. So next we go to another type of solution stoichiometry. Here we have 2.5 grams of iron are mixed with 18 milliliters of a 0.32 molar solution of chromium. This is let me fix some things here, some typos here. This should be zinc. That's what happens when you copy and paste. So zinc chloride solution, how many grams of zinc are formed? I'm going to fix this. There we go. So just a few corrections there. So we have 2.5 grams of iron. We mix it with 18 milliliters of a 0.320 molar solution of zinc chloride. How many grams of zinc are formed? So we're given information about both reactants. So we have to determine which one is the limiting reactant, and then from there determine the theoretical yield of zinc. So we're going to be doing the same thing for both iron and zinc chloride. We're going to determine the moles of zinc produced by iron and the moles of zinc produced by the zinc 2 chloride solution. So we got to determine, which one is the limiting reactant. So we're going to do two sets of calculations. The first one, we're going to take the mass of iron, convert it to moles of iron, and then to moles of zinc. Then for zinc chloride, we're going to take the molarity of the zinc chloride solution, convert it to moles. Then once we get the moles of zinc chloride, we're going to convert it to moles of zinc. So with iron, we have 2.50 grams. We got to divide by the molar mass. Now we have moles of iron. Now if we look at the mole ratio, 2 moles of iron produce 3 moles of zinc. And now we can determine the amount of zinc produced by iron. We do the same thing for zinc chloride, but instead we start with 0.320 molar. So remember, molar means moles over liters. So we have 0.320 moles. Now, let me move that. And since it's molarity, it's moles per liter. Now the first thing we need to do is convert the moles per liter to moles, and we know that there's 18 milliliters. So we convert 18 milliliters to liters. So molarity times volume gives us moles. So see here, the liters cancel out. So now we have moles of zinc chloride. We look at the ratio. It's 3 to 3. Now we see which one produces the fewer moles of product. So by looking at this, we see that the zinc chloride solution produced the fewer moles of zinc, so it's our limiting reactant. So then we just convert the moles of product produced by zinc chloride into grams. The theoretical yield is 0.377 grams of zinc. So again, since it gave us information about both reactants, we had to determine which one was the limiting reactant, and then from there, we had to find the theoretical yield. So the reason we divided for zinc chloride, we have the moles of zinc, the molarity of zinc chloride multiplied by the volume would give us the moles of zinc chloride. So to go from moles of zinc chloride to moles of zinc, we have to multiply by the mole ratio. So there's 3 moles of zinc chloride produces 3 moles of zinc. And so that converted the moles of, it's hard to, I'll squeeze it in, but these are moles of zinc chloride here. So we have, the molarity is 0.32 moles of zinc chloride in 1 liter. We multiply it by 0.018 liters, we just get the moles of zinc chloride. So see here, the liters cancel. Now to get rid of the moles of zinc chloride, we have to use the mole ratio to convert it to moles of zinc. So then these two cancel, and what we're left with is moles of zinc. Now since it's 3 to 3, the moles of zinc chloride equal the moles of zinc. Next we have another solution stoichiometry problem. We want to know how many milliliters of a 0.45 molar solution of lithium hydroxide is needed to titrate 50 milliliters of a 0.35 molar solution of carbonic acid. And it gives us the balanced chemical equation. So again, what we're looking for is volume of lithium hydroxide. And of course, it needs to be in milliliters. So to find volume of lithium hydroxide, volume equals moles times molarity. So if we know the moles of lithium hydroxide and we know its molarity, we can find the volume. Well, the molarity we know is 0.45 mole. But the moles we don't know. So now we have to use the other information given to us to find the moles of lithium hydroxide so that we can determine the volume of lithium hydroxide needed to titrate the 50 milliliters of 0.35 molar carbonic acid. Now, titrate is a way of just saying reacts. So when you have an acid base in a reaction, we call it titration. So you're seeing how much acid or base is needed to completely react or neutralize the acid or base. So here we want to know how many milliliters of lithium hydroxide we need of this solution to neutralize all the acid in this solution. So what we're going to do is we're going to find the moles of carbonic acid. So use molarity and volume of H2CO3. We're going to find moles of H2CO3, and then we can find moles of lithium hydroxide. Then once we find the moles of lithium hydroxide, we're going to determine the volume of lithium hydroxide needed. Set up my train track. So I'll start with volume. We have 50 milliliters. Again, 50 milliliters, we got to convert to liters. So we'll start with liters here. Now for liters, we know that 1 liter is 0.35 moles of H2CO3. So that's the molarity. See, it's a 0.35 molar solution, which means there's 0.35 moles of carbonic acid in 1 liter of solution. So notice here, the liters cancel. Now we need to use the mole ratio. So 2 moles of lithium hydroxide is needed for 1 mole of carbonic acid. So it's a 2-to-1 ratio. And notice now that the moles of carbonic acid cancel out. And so now we can determine the moles of lithium hydroxide. And we get 0.35 moles of lithium hydroxide. Sorry, 0.035. Okay. So now we know the moles of lithium hydroxide. We can find the volume of lithium hydroxide. So volume is moles times molarity. This is going to put it in liters, then we have to convert it to milliliters. So you would need 15.8 milliliters of this solution to completely titrate 50 milliliters of a 0.35 molar solution of carbonic acid. And so in this example, we have a precipitation reaction involving 300 milliliters of a 0.87 molar solution of aluminum nitrate is reacted with excess sodium carbonate solution. So again, excess means there's more than enough sodium carbonate to react with all the aluminum nitrate. What is the percent yield of the reaction if 21.3 grams of aluminum carbonate was produced? So in this problem, what are we looking for? We're looking for the percent yield. That's what we're looking for out of this problem. And we know that percent yield equals actual over theoretical, actual yield over theoretical yield times 100. So if we know the actual yield, we know the theoretical yield of aluminum carbonate, we can find the percent yield. So what do we know so far? We know the actual yield. That is 21.3 grams. And I apologize. Aluminum carbonate is written wrong here. It should have a 3 there. Molar mass is right, but the formula was wrong. So we know the actual yield of aluminum carbonates, but the theoretical yield of aluminum carbonate is question mark. So now we have to use the other information given to us in the problem to solve for the theoretical yield of aluminum carbonate. So what we're given is the volume and concentration of aluminum nitrates. So from the volume and molarity of aluminum nitrate, we're going to find moles of aluminum nitrate. And then we're going to find moles of aluminum carbonate. Once we find moles of aluminum carbonate, we can find mass of aluminum carbonate. And so the mass of aluminum carbonate that we find is called the theoretical yield. So once we know the theoretical yield, we can plug it in because we already know the actual yield, and then we can find the percent yield. Let me set up my train tracks. I'll leave plenty of space for this one. So we start with the volume of aluminum nitrate. Again, the volume has to be converted into liters. So we start with that. And so we know that we have a 0.87 molar solution of aluminum nitrate. That means there's 0.87 moles of aluminum nitrate for 1 liter. Notice here that the liters cancel. Next, we want to convert moles of aluminum nitrate into moles of aluminum carbonate. So notice here, for the equation, 2 moles of aluminum nitrate give us 1 mole of aluminum carbonate. So it's a 2-to-1 ratio. 2 moles of aluminum nitrate, 1 mole of aluminum carbonate. So notice here that the moles of aluminum nitrate cancel out. Next, we want to convert the moles of aluminum carbonate to grams. So we're going to multiply by the molar mass. So 1 mole of aluminum carbonate is 234 grams of aluminum carbonate. So again, notice that the moles of aluminum carbonate cancel out. And we get 30.54 grams. Again, this is called the theoretical yield. Double check. So now we have the theoretical yield, and by the way, the theoretical yield should be greater than the actual yield, which it is, so that's a good sign. So to calculate the percent yield, it's actual over theoretical times 1. We get about 69.7%. So that would be the percent yield of this reaction. So again, what we were looking for was the percent yield, which is actual over theoretical. The problem gave us the actual yield. They didn't give us the theoretical yield. So we used the other information in the problem to determine the theoretical yield. So we took the volume and molarity of aluminum nitrate, converted it to moles of aluminum nitrate, and then moles of aluminum carbonate. And from there, we were able to get the mass of aluminum carbonate, which is the theoretical yield. And so then we were able to find the percent yield of 69.7%.